then again you have 0. But as soon as you start moving inside, let me use dot lines. The value of this, if you multiply them and sum them, integrate them, the value is not going to be 0. It's going to change somehow, like, I don't know exactly, but it's going to be like this, and then again like this, and this. Eventually this guy is going to move out, right? It's going to go. So when it moves out, it's 0. So this is the convolution of these two signals. That's the kind of representation. What's that integral? Yes?
Is the convolution the function that you drew on the bottom, or is it the integral of the function on the bottom?
It's the integral. See this minus infinity, f tau. See, this is the moving part. Actually, if you want to move f, you should move it this way. You should do it this way. G tau, f t minus tau d tau. So this way, your f is moving. You see this phase shift, this time shift? You're shifting it and multiplying by g, and then the answer is g actually convolve f. You can do vice versa. But what I showed you was this. I kept my g fixed over tau. Okay. And then I am, so over t side. Okay. What I'm doing is I'm moving my f step by step, delaying it, right? Until it reaches here. So what it does actually is trying to test your system. It's trying to see if this is your, you don't know about impulse function, right? Impulse response. So it's maybe too advanced. This is like your impulse response. Okay. If you have a system which is linear time invariant, right? One way to characterize your system is to send a, you know, delta function? Impulse function, sorry, not delta. Impulse function? Okay. Impulse function has only value at one certain time at t equals 0, and the value goes to 0 the rest. So if you send this signal to any LTI system, the response of the system has many information about how system reacts. And the reason is this, I was going to teach it now, and I can write it for you. Delta in frequency domain translates to 1. You know what 1 means? What 1 means in Fourier domain? No. It means that it covers every single frequency. So it's this 1. DC. The frequency is the, so if I call it h omega. Not h omega again. It's a Fourier transform of delta t. Okay, in f, in omega. It's 1. The value is going to be 1. So it has every single frequency. So why this is important? Because if you send delta to your system, you're testing your system, the reaction of your system with every single frequency, because it covers it covers all the frequencies. So your system is tested. So whatever the behavior of the system is the behavior, is the property of the system over a wide range of frequencies. If I send a cosine in here, and whatever response was, I could just talk about one single frequency, right? Because this is omega 0 t. But this delta t has a wide range of frequencies. So when my system behaves or reacts based on this input, I can use this in future for any other signal. And how? I can use this convolution. I can use this and judge what's going to be the answer of this system to ut. I can judge the response of this signal to delta t. I can judge the response of this signal to any shape, rect function. Just having the response to ht. That's the beauty of convolution. That's where convolution comes into the picture. And it's a mathematical derivation that if you have any signal, if you convolve it with ht, the response of system for one delta t, this is the response of, okay, let me write it in here, ft. Now instead of delta t, I'm using ft. And what I'm getting is yt, right? ft, yt. So ft convolved with this ht, this ft, get convolved with this, provide this. Always true. As long as you have LTI system. That's why we need convolution theory. So that h omega that you saw before, we talked about, that's the response of the system when you use one impulse function to excite it. If you excite any system with impulse function, what you get as output is called impulse response, and it's called h. And if you transform it to omega domain, that's h omega. You used it, right? But you didn't know where did it come from. In real life, they do it that way. You have a very narrow pulse, call it impulse function, and you send it to your system, and then you look at the response. You measure the response, and that response is ht.
So this convolution is basically the same thing that we learned last time, but because it's not periodic anymore, you have to do something a little bit different to it.
No. If it doesn't matter if this ft is periodic or not. It's the same. The rules are the same. Always you need this convolution. If you have a periodic signal which goes here, instead of using f omega and h omega, right? You use fn h omega. That's the only difference. Fn is no longer continuous, right? It's discrete. That's the only, because your signal is not continuous. But your h omega is different. It's from your system. Signal and system. That's what you're learning, right? We analyze signal, and then we analyze system, and then the interaction between system and signal. That's what we get as output. It's too advanced maybe. Just forget about it for now. Let's move on to calculate Fourier transform of a few, or yeah, I think a few only I can do. Yeah, a few popular signal. Okay, this is E minus AT UT. Let's see that we can do this or not. So if I want to do this, what I should do? If I want to calculate F omega, you guys know, right? What do you do? What do you do if you want to calculate F omega for this?
Use the integral.
Exactly. Use the integral. Okay. Very good answer. And my assumption is A is bigger than 0. Okay? So if I use the integral, I will have this. And you guys know ut is 0 for t smaller than 0, right? So this integral will turn to, we can convert it to this. Right? And if I do this integration, actually is this. Minus a plus j omega t divided by minus omega, going from 0 to infinity. And this is going to give me this one. So I could calculate that this guy, E minus AT UT, the pair for this is 1 over A plus J omega. This is important. You should memorize it, or you should know how to calculate it again. For A bigger than 0. Now let's do the same example, but this time I call it G for now. GT is going to be E alpha T, I believe U minus T maybe. To do this, just make sure that, yeah, E alpha or AT U minus T, and A is positive, So to do this, I can do the same thing. I can do through all of this calculation. But remember why I wrote those properties on this blackboard. This is actually time scale version of this. You see it, right? GT is F minus T. And I can use time scaling property, right? Yeah, remember it? 1 over absolute value of minus 1 F C omega divided by C, which is minus 1. My C in here is minus 1, right? I scale it by that. So if I do this, my F omega was calculated here, and I do this, I'm going to get this. Done. I don't need to do any calculation, extra calculation. So GT called E alpha T U minus T equivalent to 1 over A minus J omega. And the last, maybe, I mean, if you are, I'm going to keep this one. Here's this part. Now what about this guy? E minus A absolute value of T. This is PT. Can I do this? Yeah, can I calculate? This is one of the usually most difficult one when you look at it, but it's not that difficult to calculate. Why? Because I can write this as agree? Can do that, right? Now I can use addition property. So this signal P in Fourier domain, P omega, is going to be this guy, which was F omega, sorry, G omega, plus F omega. This is 1 over A minus J omega plus 1. And if I keep calculation, that's what I did. See, if I plot that, let's plot this one. It's interesting to learn, to see this one. E, and I assume A is 1 to just do the plot. E minus absolute value of T. If I do this, this is the shape. Okay. If I look at it in Fourier domain, omega, T omega. You plot it, you're gonna see these two are not so far away, almost like each other. Extended from minus infinity to plus infinity, see this going. And same in here. This is a nice function. I don't have enough time. I like to go over more functions, but please study sinc function. It's one of those most important functions that I really like to go over it, but you have to do it because you need it. Sinc power T. What is the transform for it? And I can write it down for you. It's not a direct function. Okay, and then again, the other way, use rate function, let's say T, and calculate T over tau maybe. Maybe this is sinc T tau. Then calculate the Fourier pair, which is going to be sinc something omega, a function of omega. So this is in your book, you can go over it. And it's very important to know this too. Sinc, rect, sinc. For those of you who like to study digital